Okay, so we're in the middle of this example. Get out of here. We had this rudimentary caveman-style boomerang from the difficulty of calculating the moment of inertia and the center of mass of this. I'm glad we didn't do a more detailed boomerang figure. And the thicknesses, so it was 5 centimeters. Thickness everywhere. And this was 0.2 meters, 20 centimeters. This was 0.25 meters. And at this instant, it has an angular velocity of 20 radians per second. And it just smacked into the wall, a wall over here. And that reaction force is 800 newtons. The mass of this thing is 0.1 kilograms. And this is the point P, and we want to calculate the acceleration of the point P. Maybe there's like a bug on that point, and we want to see if he's going to be able to hang on. Okay, so first of all, I gave you that it has an angular velocity of 20 radians per second. Why don't we calculate that from the forces and stuff? This is dynamics, right? Okay, good. Okay, I was afraid I was in the wrong class. Yeah, why don't we calculate that angular velocity? Because there is no relationship between forces and angular velocities. Well, in 2 dimensions, there's no relationship. If you remember, or you've heard of precession and stuff like that, there is a relationship between precessions and forces and stuff, but that's another tale for another day. Okay, so that has to be given. So think of like forces instantaneously don't affect velocities, okay? If you integrate forces over time, they affect velocities. But at a single instant, those are totally independent of each other. Forces and couples at a single instant only affect accelerations and angular accelerations, okay? So that has to be given. Yeah, I mean, that's the end of it. That has to be given. If it's not given, you can't calculate this stuff, okay? If it's not given, it probably means you're supposed to assume it's 0, but that has to be given in some way or other, you know? And what about the fact that, okay, we know how fast it's moving. Why can't we just calculate the force? So it says 800 newtons is applied by the wall. Why can't we just calculate the force that something's spinning that fast up, you know, what the contact force is? Yeah.
We don't know what it's impacting.
Yeah, that's right, exactly. I mean, if it's impacting a cloud, then that force is going to be small, and it's going to be spread out over a long time. If these are perfectly rigid and the wall, if this boomerang is perfectly rigid and the wall is perfectly rigid, that force is infinite, you know? So this says something about the stiffness of the contact, you know? Okay? So anyways, here's where we are at this point. So remember that the steps are, so let's think of the steps. So first, is there a fixed point? No. So the about point is the center of mass. Okay, that was the first step. And the second step is to calculate the mass moment of inertia. And that ended up being a whole deal, right? But now we've done it. So we know that if our coordinate system, like in a coordinate system like this, we know that, well, first of all, we know that this mass moment of inertia was 1.09 times 10 to the minus third kilogram meters squared. And then we know that the centroid location of this thing, the center of mass location, was negative 0.081, positive 0.169. Okay? And now we're going to fill out well, first we'll do the free body diagram. We know that there's an 800 Newton force here. And the center of mass is somewhere like that. And that's where the weight force is applied. It doesn't feel very satisfying applying a weight force where there's no material, but that's just how it is if you're going to represent it as a point force. And this force is 0.1 times 9.81, so 0.981 newtons. Any other forces acting? Yeah, once you've applied the weight force and you've gone around the boundary looking for contact, you're done. So now we can go to the table. And I'm going to move this over a little. So rho, force, moment. And we only have two forces we have to deal with. Now, that rho vector, you should definitely remember, be able to recite in some way what the mathematical meaning of that rho vector is, okay? So that rho vector is a vector that goes from the about point to the location of the force, okay? So I'll start with mg. What is the vector from the about point to where that weight is applied? I'm making this sound like you have to do something, but you don't. Anytime your about point is the center of mass. Zero, yeah. Anytime the about point is the center of mass, your weight force is applied at the about point and your rho vector is 0, okay? So, and the force vector is 0, negative 0.981. That's pretty small, that's not going to have much of an effect compared to the contact force. And then the moment about the z-axis is 0. But now we have to do the 800, and that's more of a pain. Okay, so how do we calculate the rho vector for that 800 Newton force? remember this. And actually, if you look at the solutions, I think in a lot of the solutions, the table has two other columns in it. Have you noticed that? It has a P column and an A column. That's because the row vector is, the vector that goes from the about point to where the force is applied is always calculated as the coordinates where the force is applied minus the coordinates of the about point. Okay? So if you're looking for the row vector for that 800 Newton force, we have the about point listed in a coordinate system down at the bottom. You know, the one in this picture, right? So let's just calculate everything in that coordinate system and then just do the subtraction. Okay, I think that's probably the easiest way to do this. Okay, so in this coordinate system, we have to come up with the coordinates of this point here. Let's see. So that would be up 0.2, up another 0.025. So the y component is going to be 0.225. And then for the x coordinate of where that force is applied, it's going to be in the negative x direction, and it's going to be a distance of 0.2 plus another 0.025. So this is going to be negative 0.225. Anybody want me to clarify anything on that? Are you with me on that? And then we're going to subtract the coordinates of the about point, which I listed here. So minus 0.081, minus negative 0.081, positive 0.169. And so that row vector comes out to be, who wants to erase me? Negative 0.225, positive 0.225, minus negative 0.081, positive 0.169. And so what I get for this row vector is negative 0.144, positive 0.056. Anyone else get that?
Yeah.
Okay.
Last time, we took the origin to be in the bottom right corner instead of in the midpoint. Remember?
Okay.
I don't know if that.
That does matter. Yeah, that does matter. Let me look and make sure. I thought I had looked and you're right. Ah! Okay, that's easy to fix actually. Okay, so we're not going to use this coordinate system. Sorry about that. We're going to use this coordinate system just because that's what we have our information in. And so what does that change? Well, we calculated that, that center of mass location, so that's not going to change. The only thing that's going to change is our x component is going to be, our x component of where the force is applied is going to be an extra, plus an extra 0.025. So this is just going to be negative 0.25. And that's going to change this one. So that is 0.169. Okay, now you agree with that one? Okay. Any questions about calculating that row vector? Are you following what I'm saying there? You can always use this calculation. So in the old days, I used to have people write out a table that had a column for the coordinates of P, a column for the coordinates of A, and then you just subtract those two and it gives you rho. It's sort of nice, but I just got away from doing that. It's a more complicated looking table. I had to give you a mnemonic device for remembering the order of the columns. And it was P, A, rho, F, M. So I said, it's been a long time, pancake artists row for marzipan. So I imagined this like artisanal pancake maker who lived on an island and had to row to go get the marzipan for his fancy pancakes. I also, before that, the mnemonic device was Princeton athletes row for mommy, which I thought was funny, but it also had like class grievance undertones, and so I stopped doing that. So anyways, now I just do rho FM, but you can always calculate rho as P minus A. Okay, so there's our row vector. And our force vector is positive 800, 0. And the cross product of those is negative 44.8. So now we have all our loads represented. We've calculated our moments. Do we need to use Newton's second law for this one? Yes. So Newton's second law. We're going to add up all the forces. So that's all the stuff in this column. So 0, negative 0.981. Plus 800, 0 is equal to the mass times the acceleration of the center of mass. So I'll call that AXAY. Remember, that's Newton's second law says this is the acceleration of the center of mass. And we can calculate these directly from here. So we have AX is equal to 8,000. And AY is equal to negative 9.81. So the acceleration of the center of mass is 8,000. 9.81 meters per second squared. And no matter whether your about point is a fixed point or the center of mass, you use the moment equation. And that says 0 minus 44.8 is equal to 1.09 times 10 to the minus third times alpha. Negative 44.8 divided by 1.09 e minus 3. So the angular acceleration is negative 41,100 0.9. This is radians per second squared. Well, yeah, I mean, these are really big accelerations because you have a relatively rigid thing just smacking right into a wall, you know. So now we're done with the main part of this problem. Now, once you've gotten to this point, now you can look back at what specific things you're being asked for. And we're trying to calculate the acceleration of this point at the bottom. Okay? So how are we going to do that? Well, the acceleration of that point P relative to the ground is equal to the acceleration of that point P relative to the body's center of mass plus the acceleration of the center of mass relative to the ground. Okay? This is this, right? That's just the acceleration of the center of mass. And we got that from Newton's second law. And this, now if you imagine that, so with these relative motion equations, the acceleration of P relative to the center of mass, you can imagine that the thing is fixed at the center of mass and you're just calculating the acceleration of P. So this is the watermelon equation. You know, this is going to be all ripe watermelons will rot. Circular motion. Okay? So we already have the acceleration of the center of mass, the acceleration of P relative to the center of mass. Is we're going to use this. That omega you can't calculate, that has to be given, and it is. So omega given in the problem was positive 20 in the z direction. The r vector, so just like I said, you should be able to, if you're asked for the definition of the row vector, you should be able to come up with it. You should be able to come up with the definition of r also. That is a vector from the center of the circular or spherical motion to the point that you care about. Okay, so, that is, so the vector that we want, I'm going to draw it and then erase it, but it goes from the center of the circular motion is the center of mass, and we want the vector that goes like this. Okay. We've already come up with that today, or we've come up with the opposite of that today, when I thought that the origin was at that point P, you know. But one thing you can do here is, so you always can just add up vectors. Like if I hadn't mistakenly already calculated that, I could calculate the vector going from that center of mass to the origin, and then the vector going from the origin to the P we want, and just add those two vectors up. Trying to erase this without losing my, forget it. It looks good there. Okay, so R is, So this is going, okay, so what we had before was negative 0.225, positive 0.225. That goes from the point P to the center of mass. So the opposite of that goes from the center of mass to the point P. So this is positive 0.225, negative 0.225, and then 0 for Z. Anyone have any questions about R? And then alpha, this is the one that we calculated from the kinetics. This is the only one all those steps of the kinetics, this is the only thing we needed it for in this calculation, you know. Well, that's not true. We also needed to know the acceleration of the center of mass. But 0, 0, and then in the Z direction, negative 41,100.9. And so the acceleration of P relative to the center of mass is equal to 0, 0, negative 41,100.9 crossed with 0.225, negative 0.225, plus 0, 0, 20 crossed with the quantity 0, 0, 20 cross 0.225, negative 0.225. 8,000, negative 9.81, and you get an acceleration of 1031.55, negative 2243.86 meters per second squared. Any questions about that? All right, well, that's the end of what I'm going to say about just individual rigid bodies. So the next thing we're going to do is use rigid bodies to calculate forces and accelerations in linkages. So a linkage is, and we're not going to start this today, but I'll sort of introduce it. I don't know, this is one of my two favorite topics in this class, linkages. This is so useful. It's useful in any kind of machines, engines, anything like that. We're only doing it in 2D. So it has to do your calculations this way, it has to be a planar motion, but that's a lot of important stuff, you know. A collection of bodies connected by joints that's in static equilibrium what's that called? The things we did in statics. Structures. if you have a structure and you take away one restriction on motion somewhere, you have a collection of bodies with joints that are not in static equilibrium. You know, imagine taking away, like, you have this truss, and instead of a pin joint in the middle, you make it just a frictionless contact or something. You give it one extra degree of freedom. Now you have a collection of bodies connected by joints that's not in static equilibrium. And that's a linkage. Okay, so like, for example, you can have all sorts of crazy stuff. But imagine something like this, where this is a pin joint. Okay. Now, if you apply a force, this thing is going to have accelerations, and that's what we're going to calculate next. Okay. And the trick to this is identifying the bodies that have fixed points and the bodies that don't have fixed points. Okay, so let's look at this for a second and think about what has fixed points. So the long piece here, does that have a fixed point anywhere? Yes, that is undoubtedly a fixed point. Okay, this spot on that long member has no acceleration, no velocity in our coordinate system, in our inertial coordinate system. What about this one? It does have a point that's fixed to something else, okay? But that is not fixed in our coordinate system. As this thing moves, that point's gonna move, okay? So this one, we're going to have our about point be at the hinge. And this one, we're gonna have our about point be at its center of mass. Okay? So that's what we're going to get into next. And obviously, as you can imagine, it's a major bookkeeping issue as these things get bigger. But if you can just remind yourself that what you're doing is a bunch of rigid body problems, and then you come up with a system of equations that you solve at the end, and we'll use reduced row echelon form for that. Okay? All right, that is all I have to say. Who wants to know why you can only have your about point be at the fixed point, at a fixed point or the center of mass? Has that been like burning at you?
Because then you can't use the second law equation at all if it's rotating.
No, that's not, Newton's second law still applies. It's the rotational equation that doesn't. And why doesn't it? You know, that's sort of the question. Well, this is bonus material. This is outside of the for special interest. Why in dynamics does the rotational equation only work for A equals fixed or A equals the center of mass? Well, the answer comes from, like, where does the rotational equation come from in the first place? Okay, so imagine you have a random collection of particles. And let's say that we have, I equals 1 to n of these particles. Okay. Then for each one of those particles, we start with Newton's second law. That's the starting point. Okay. So for each one of these particles, the total force on that particle is equal to the mass of that particle times the acceleration. Right? That's the starting point. And we can rewrite that as this is equal to the mass times the time derivative of the velocity. Okay. And now let's choose some point A. Okay. And then rho I is the vector from A to particle I. Okay? Well, if these two things are equal, now we can say, we can take rho cross each side individually. So we'll go rho I cross Fi is equal to rho I cross Mi Vi dot. Okay. And for rigid bodies, the time derivative of the angular momentum is equal to I alpha. Okay. So the question is, when is this thing rho I cross Mi Vi dot equal to the angular momentum time derivative? And so that's what this question comes down to. And the angular momentum time derivative is the time derivative of, so this is the definition of the angular momentum. This thing is h. And then we'll take the time derivative of it. And if you take that time derivative, you get rho I dot cross MVI plus rho I cross MVI dot. Okay? All right, well, our question then boils down to, when is this equal to this? You know, for what A are these equal? Okay, so we're looking for like, when does rho dot cross, I'm not going to go over with this, but when is this equal to 0? Okay. What?
So rho dot is equal to 0?
it doesn't have to equal 0, but the cross product does. So one way that this can equal 0 is if rho dot is parallel to V, right? So remember rho is equal to Pi minus A, okay? And so rho dot is Pi dot minus A, which is Pi dot is V. Pi dot, no, I made it here, this is important. Pi dot is equal to P dot minus A dot. Okay, so if it's fixed, what's A dot? Nobody's listening anymore, this is. And so rho dot cross MV is equal to V, these all should have I's, this is for one individual particle, V cross MV, which is equal to 0 because of how the cross product works, okay? The one for, okay, so what we get is that MA net is equal to HA net dot if A is fixed. What if A equals the center of mass? Well, it turns out that you get the same result in the end, as you can imagine. And those are the only two cases where this relationship holds. Okay? So this one actually is the more complicated of the two. But that's where it comes from. And where, like, I don't know. It's kind of cool to see, I think. It's not anything that you'll need to use in this class. I'll never bring it up again, but the two take-home things, I guess, that are sort of useful for understanding with this. First of all is that rotational Newton's second law, the moment equation, comes directly from starting with Newton's second law and taking the cross product of rho with both sides for each particle. So that's kind of cool. Maybe you'd never heard that before. And then the second thing is, okay, there's only two cases where this circled term reduces to H dot, and that is for A fixed and A at the center of mass. Okay, that's all.